I welcome you all to another video tutorial session on finite element procedure for solving structural engineering problems. In today's video, we are going to use the finite element procedure in solving a 3D truss system using Matlab. In my previous video, we've dealt with plain truss system using the finite element procedure by using Matlab and also by using the ANSYS software program. So in today's video, we are going to look at how we can use the finite element procedure for the 3D truss system. The problem we are going to solve in this lesson actually shown on the screen. The problem has three elements. First of all, before I explain the problem that we are going to solve in this tutorial lesson, I want to give a brief introduction of what a 3D truss system is. 3D truss system is actually a very important structural system in civil engineering. It has many applications. It has it has several applications in civil engineering industry. The 3D truss system is used in roof structure. In roof structure where you want like clear span of say 40-50 meters, and the best system to use in this case scenario is actually a 3D truss system. They said that when that the 3D truss system for when applied to roof structure can span up to 90 meters if the support are properly placed around the structural system. So the maximum length is said to be 90 meters for a 3D truss system. Also, the 3D truss system can also be found in the electrical industry. They are used for they are seen in electrical mass structure. These are structures that carries overhead cables that supplies that carries high tension electric currents from from where the electrical current is generated to over long distance. So the 3D truss system is also used in erecting electrical mass structure. I think I have images of this structure on my computer. I think I should show you. This is an example of a 3D roof truss system. You can see the truss system here. Um, um, Actually, this is a front view of the 3D roof truss system. You can see the clear span of the support. This clear span, if I should estimate it, this is around 20 meters. So you can see the application of the 3D roof the 3D roof truss in this image. This is an electrical mass structure used to carry electrical cable. So this is also an example of a 3D truss system. This another roof truss. This another roof truss, a 3D roof truss. And if we should note something, we have the connectors. The connectors of roof truss. There is a special type of connectors that is very common for connecting the 3D truss element. They call it the mirror node connectors. This circular bulb here, let me see if I can get another one. It's also seen here. Let me check the internet for a clear image of the mirror joints used in 3D truss systems. So this is an example of a mirror joint. It's actually a ball-like component that connects the truss element together. So this is the technology they use to connect the 3D truss elements together for a roof truss system. The mirror joints. This is it here. The mirror joints. So this is the joint which is widely used in 3D roof system. So this is a brief introduction of application of the 3D source system. Now we are going to solve numerical problem for a 3D source system. So let's consider this is a structural problem. This structural problem consists of three elements as we see, three source elements, and we have a point load at node D, 70 kilonewton at joint A, joint B, and joint C. The joints are rigidly fixed. That is, there is no movement in the X, Y, and Z direction. You can see the notation. There's a form of notation at node A, B, and C, denoting that those nodes cannot move. They are rigidly pinned. So those are our support position. So this is the problem we're going to solve in this lesson. And to solve a problem like this, the first thing you need to do, you need to define the finite element model for this problem. And what we need to do first, we need to number our elements, we need to number our nodes, and we also need to number our degree of freedom. For a 3D source system, unlike the 2D source system, the 3D source system at each node has 3 degrees of freedom. As you can see here, at this node, which I call node 1, we have 3 degrees of freedom. Degree of freedom in the 3 coordinates direction. Degree of freedom 1, 2, 3. So each coming to Z. Each node has 3 degrees of freedom. So aside from that, when solving a 3D source problem, the first thing we need to do, we need to define our final element model. So the first thing I'm going to do, I'm going to number our elements. We have 3 elements in this problem. So you can see here I numbered this element with number 1. The number in the triangle represents my member number. So this is element 1. This element here is element 2. This element here is element 3. So once you have done that, we need to also number our nodes. So I'm numbering this node here, node 1. I'm numbering this node here, node 2. I'm numbering this node here, node 3. And I'm also numbering this node here, node 4. So once we have done this, we can now also define our degree of freedom numbering. And you number your degree of freedom in increasing ascending node number. So I'll start from node 1. This is node 1 here. So and I told you that each node has 3 degrees of freedom. So in the X, Y, and Z direction. So this 1 is degree of freedom in the X direction. This 2 is degree of freedom in the Y direction. This 3 is degree of freedom in the Z direction. I'll move once you have numbered the degree of freedom in node 1, you move to node 2, and you also number the degree of freedom at node 2. So we have degree of freedom 4, 5, 6. At node 3, we have 7, 8, 9. At node 4, we have 10, 11, 12. So we have 12 degree of freedom in this problem. So once we have done this, there's also we also need to define the direction of each of our elements. The direction, defining direction indicates the start node and the end node of each element. For element 1, I indicated the direction is in this direction. You can see this arrow here pointing from node 1 to node 4. So because the arrow is pointing from node 1 to node 4, it means node 1 for my element 1 is my start node, while node 4 is my end node. For element 2, the arrow is pointing from node 2 to node 4. This means node 2 is my start node, while node 4 is my end node for element 2. While for element 3, the arrowhead is pointing from, I chose the arrowhead to point from node 3 to node 4. So this means node 3 is my start node, while node 4 is my end node. So we need to indicate the direction of our arrow, and direction can be in any order. It depends on how you define it. So once we have done this, we also need to define our coordinate system. In this problem, I'm using this coordinate system. X in this, my positive x direction is pointing to the right. My y direction is in this direction, while my z direction is upward. And for this problem, I'm taking my node 1 as my 0, 0 coordinate. You can put your 0, 0 coordinate at any point, but it is advisable you put it at a point that is convenient for you to determine other node points. Like I chose node A as my 0, 0 coordinate because I can easily reference other I can easily reference other I can easily determine the coordinate of other node points. That is node point B, C, and D. So if node A is my 0, 0 coordinate, node B from 0, 0 coordinate here, 0, 0 coordinate, like the first one is my x coordinate, the second value is my y coordinate, and the third value is my z coordinate. For this, in this image, they actually use this as their coordinate, but I'm using something different. Here they define the z pointing downwards as their positive axis, but me, I'm using z pointing upward as my positive value. That's just the difference. But the order of the coordinate is x, y, z. So if coordinate A is 0, 0, 0, what is the coordinate of B? Coordinate B, the x component is 6. We see from this point to this point is 6 meters. So the x is 6. The y for node B is the y is the distance from this point to this point, which is 8 plus 4, 12. 12. And the z is 0 because node A and node B, they are in the same vertical level, as we see in the diagram. So this is the coordinate definition for node B. For node C, the x will be the x component, which is in this direction, will be the distance from here, this point, to this point. And that distance is 6 plus 2 plus 3, which is 11. The y coordinate will be distance from here to here. Distance from here to here. This distance here. So, and that value is 8 meters. The z component, A, B, and C, they are in the same level, so the z component is 0. For node D, we see that the x component for node D is distance from here to this point for node D, and that is 6 plus 2, 8. So the x component is 8 meters. The y component is distance from here to this point, this distance here, and that distance is also 8 meters. And the z component, the z component of D is minus 4. Why is it minus 4? Because D is not in the same level with A, B, and C. D is below A, B, and C by 4 meters. So that's why it's minus 4. So this is how we define the coordinate This is how we define the coordinate values for each node. So this is our finite element model for this problem. So you can see that's 4 nodes, 12 degree of freedom, 3 members, and I've specified the coordinate system on the drawing, which you see it here 0, 0, 0 at node 2, 6, 12, 0 at node 3. Look at the value here, and at node 4, this is the value here. So this is the first step we need to do when we are analyzing 3D truss system. So now I'll move to the next slide. Um, Going to front. So like every finite element problem, you see for one dimensional problem as is stiffness matrix. For the plane truss problem, that is stiffness matrix. The 3D truss system also has the 3D truss problem also has its own stiffness matrix, and the stiffness matrix is defined by this 6x6 matrix. Where Cx, Cy and Cz are actually cosine angle in the x, y and z direction respectively. I'm going to explain what that means. So this is, we should just know that the local stiffness matrix of a truss element is a 6x6 matrix in this form. The Young modulus multiplied by the cross-sectional area divided by length multiplied by this matrix. That gives the local stiffness matrix of the 3D truss element. So let's assume we have this 3D truss element, and we define the node as shown in the image. Here we have node 1 and we have node 2. This is the A represent the cross-sectional area of the element, E represent the Young modulus. This L representing the length of the 3D truss element. And let's say our coordinate definition at node 1 is x1. Is x1, y1, z1 for coordinate 1. For coordinate 2, the coordinate definition is s2, y2, z2. So and for this element, we also need to let's say the direction of arrow is in this direction as shown here. That is pointing from node 1 to node 2. It means node 1 is our start node and node 2 is our end node. So if we are choosing this direction, it means we need to define CS, CY, CZ in this order. CS is actually the cosine angle in the x direction. CY is the cosine angle in the y direction. CZ is the cosine angle in the z direction. So like the cosine angle in the x direction is actually just equals to the difference in length in the x direction divided by the overall length. The cosine angle in the y direction is the difference in the y direction between the two nodes divided by the overall length. Likewise, the cosine angle for in the z direction. So because the arrowhead is pointing from node 1 to node 2, it means that when we are calculating cosine angle for CS, CY, CZ, we subtract the coordinate in the end node from the start node. Like this CS here, for this problem here, in which our arrowhead is pointing from node 1 to node 2. So for CS, the CS will be defined as S2 minus S1 over the overall length. The CY will be defined as Y2 minus Y1 over the overall length. The CZ will be Z2 minus Z1 over the overall length, where the length of the member is actually the square root of the difference in the coordinate points, the square of the square of the different, the addition of the square, the addition of the square the addition of the square of the coordinate axis, like s2 minus s1 square plus y2 minus y1 square plus z2 minus z1 square, then we'll find the square root. So that gives us the length. So this is when you're assuming the arrowhead is pointing from 1 to 2. Assuming the arrowhead was pointing from 2 to 1, that means 2 is my start node and 1 is my end node. So it means that my cosine angle in the x direction will be s1 minus s2, not s2 minus s1, s1 minus s2. The same thing for cy, y1 minus y2 minus y2. Same thing for cz, s1 minus z2 divided by l. So this is a very important concept we need to understand. If we miss it, we will get wrong values. We won't get the right answer. So we need to understand how to define your finite element model in this manner. This is actually the simplest way. You just need to understand the trick. It's just a trick. You just need to understand it. So I'll move to the next slide now. As I said, this is before moving to the next slide. So this is the local stiffness matrix for a truss element, a 6 by 6 matrix consisting of a cosine angle in the x, y, and z direction, Young modulus, cross-sectional area, and the length of the element as variables. I'll move to the next slide. So this is another important slide. So still on the element arrow definition. So assuming I define my finite element in this manner, that is arrowhead pointing from node 1 to node 2. It means node 1 is my start node, node 2 is my end node. So my 6 by 6 matrix, which is this, how I number the rows and column? You will number the start node, the degree of freedom in the start node first, and then we number followed by the degree of freedom at the end node. So because the arrowhead is pointing from 1, so I will start my numbering from the start node, which is node 1, and the degree of freedom at node 1 are 1, 2, and 3. So 1, 2, 3. You see it, followed by the end node 4, 5, 6. The same thing for the column 1, 2, 3, 4, 5, 6. But when the arrowhead is pointing from 2 to 1, that means 1 is my end node, 2 is my start node. So you always start your numbering of your matrix from the start node. Because 2 is my start node, I'll start my numbering like this: 4, 5, 6. And see 4, 5, 6. Then I will number the degree of freedom at the end node, which is node 1. 1, 2, 3. You do the same thing for the column: 4, 5, 6, 1, 2, 3. So this is very, very important in the finite element procedure. So once we understand this, I'll move to the next slide. I actually wrote a code on Matlab which we can use to determine each local stiffness matrix of a 3D truss element. So as I said before, this is the stiffness matrix, local stiffness matrix of a 3D truss element. So I wrote this code on Matlab to compute the stiffness matrix of each element. So K is the function that returns the stiffness matrix of the truss element. I named the function GSME2. You can see it has 5 input variables: x, capital letter X, Y, Z, E, A. Here my x is the difference in the x coordinates between the node. My y is the difference in my y, let me highlight it. This x here is the difference in the x coordinate. The um the the x coordinate in the end node minus the x coordinate in the start node. The y is the difference in y coordinate. The end coordinate, the y coordinate in the end node minus the y coordinate in the start node. Same thing for z. E is the Young modulus, A is the cross-sectional area. So once this is inputted as input variable in the function, the length of the length coming the length of the member gets calculated in the function by this Matlab line of code. L is denoting the length, like the square root of x squared plus y squared plus z squared, which x and x, y, z are what was entered there in the input variable. So once the length is calculated, we can calculate the cosine angle in the x, y, and z direction, which will be given by capital letter X divided by L, capital letter Y divided by L, capital letter Z divided by L. Note that X is the difference in the X coordinate, that is like S2 minus S1. Y is also the difference in the Y coordinate, Y2 minus Y1. Same thing for Z. So once Cx, Cy, and Cz is calculated, we can now compute our local stiffness matrix, which I define here, the 6 by 6 matrix. So Matlab will calculate this local stiffness matrix and returns the value for us. So I ran this function on Matlab, and I ran this function on Matlab. I say in the command window, I say I created a value k1. I called the function. I entered the 5 input variable. This is the difference. 2000 is difference in x coordinate. 3000 is difference in y coordinate. 5000 is difference in z coordinate. This value is the Young modulus. This value is the cross-sectional area. So once I enter this code and I press enter, and it returns a 6 by 6 matrix to me. So this is the local stiffness matrix which was computed in the command window. So this is how we are going to compute the local stiffness matrix of a 3D truss system on Matlab. So after you understand that, you also need to we're already familiar with this, to determine the global displacement matrix of the 3D truss system. The local stiffness matrix, we need to assemble all of them together to form the global stiffness matrix. So the Ks here is the global stiffness matrix. So and the PS here is the force vector. So once we multiply the inverse of the global system matrix by the PS, we get our displacement vector. That is the global displacement vector. So it just once we compute the global stiffness matrix, we invert it and we multiply by the force vector, and we get the displacement the global displacement vector. I'm going to illustrate this on the Matlab working environment, so don't worry, you understand it better when we are working through an example in the Matlab working environment. So once we have calculated the displacement and global displacement vector, we can determine the area force in the 3D truss element using this formula here. Kk is the local stiffness matrix of the element. Take K1, local stiffness matrix of element 1, K2, local stiffness element of element 2, Kk, local stiffness element of element K. The dsk is the displacement vector of element K. If the K can be 1, if K is 1, the displacement vector of element 1. This displacement vector here is the local displacement vector for the element is a 6 by 1 matrix. That's 6. Each element has 6 degrees of freedom, 3 degrees of freedom at each node. So the DFK is a 6 by 1 matrix, the KK is a 6 by 6 matrix. So once this is multiplied together, we get a 6 by 1 matrix, a 6 by 1 column vector, and that vector gives us the forces in the XYZ in the XYZ direction in each node of the element. I'm going to illustrate how we use this formula in the Matlab working environment. Um, Actually, this is actually the graphical result of this problem. These 3D truss element here. There are three of them. So once we solve, we'll find out that element 1 is under 30 kilonewton tension force, element 2 is under 50 kilonewton tension force, element 3 is under 30 kilonewton tension force. So I'm going to illustrate that. So let's move to the Matlab working environment now. So I'm on the Matlab working environment now. So the first thing I think we need to do, we need to define our coordinate, the coordinates of each node in our problem. Let me copy an image from PowerPoint. Let me bring it closer. So the first thing we need to do, let's define our coordinate for each node number. For each node, we have 4 nodes in our finite model: node 1, node 2, node 3, node 4. So let n1 the node coordinate of node 1. So the coordinate of node 1, as you can see here, is 0, 0, 0, as already explained in the PowerPoint presentation. So you can see 0, 0, 0. Element 2, element 2, node 2. Node 2 is this node here, 6 by 12, 6, 12, 0. I'm working in millimeter. So this coordinate unit is in meters. Because I'm working in a millimeter, so I'll convert it to millimeters: 6,000, 12,000, and 0. So that's why N2 is defined as 6,000, 1,000, 12,000, and 0. And node 3 is shown here, 11, 8, 0. That's why we have 11,000, 8,000, and 0 here for node 3. N4, node 4, we have 8, 8, minus 4. So that's why we have 8,000, 8,000, and minus 400. So these are the 4 node coordinates in my final element model. So once we have done this, we need to now compute the local stiffness matrix of each element. So I'm starting from element 1. Element 1 is between node 1 and node 2, node 1 and node 4 rather. And for element 1, the arrow points, the red arrowhead points from node 1 to node 4. So node 4 is my end node, node 1 is my start node. So we define our Young modulus E. In the question, what was given as the Young modulus? Okay, 205. For this question, the Young modulus is given as 205 times 10 to the power 6 kilonewton per meter square. So we need to convert this unit to Newton per millimeter square. In Newton per millimeter square, this will be 205 times 10 to the power 3. So, sorry. So 205, let's change this to 205. 205 times 10 raised to the power 3, which is what is there. The area in our question, the cross-sectional area in our question is given as 20.7 times 10 raised minus 4. So change this value to 20. 20.7 divided by 10,000 times 10 minus 4, 10,000. Correct. So this is our Young modulus, this is our cross-sectional area. So we need to find, because I want to use this function, in this function I need to pass in the difference in my x coordinate, the difference in my y coordinate, the difference in my z coordinate. So we need to compute those differences, and that's what I did there. For s1 I say n4 n4 as I call the first element in the n4 vector, and I subtracted n1 from n4 in the first position, 1 1. Like n4 is my coordinate, and is my coordinate for node 4. So n4 1 is this 8,000. n1 1 n1 1 is this n1. n1 1 is this is 0, the first component in the vector, in the matrix, 0. So it is 8,000 minus 0. So that's why we have 8,000 here. For y1 we do the same thing. But why are we subtracting node 4 from node 1? Element 1 is located between node 1 and node 4. And we subtract the end node from the start node. And for this question, because the arrowhead is pointing towards node 4, so node 4 is our end node. So that's why it is node 4 minus node 1. So that's why this is defined as this. So the S1, Y1, Z1 is computed in this manner. The Y1 we just call the second position, N4 minus N1, but we are calling out the second element in the vectors. We do the same thing, but here we are calling the third element. The third element in the vector represents the Z value. So we do this. We then enter the value of x1, which is defined already, y1, z1, the Young modulus, which we have already defined, and the area also, and k1. And we assign this function to a variable called k1. K1 is our local stiffness matrix for element 1. So when we run this, so this is our 6x6 local stiffness matrix for element 1. So we do the same thing for element 2. Because element 2 is located, this is element 2 here, and it's located between node 2 and node 4, and the arrowhead is pointing towards node 4. It means that node 4 is our end node. So it will be n4 minus n2. So that is why in element 2 we have n4 minus n3. Okay. Wow. This is a mistake. Element 2 should be n4 minus n2. Okay, element 2 is n4 minus n2. So this is n4 minus n2, n4 minus n2, n4 minus n2. So we do this for position 1, we do this for position 2, we do this for position 3, and we enter the value here, and we run to calculate K2. K2 is the local stiffness matrix for element 2. Do the same thing for element 3. Element 3 is located between node 3 and node 4, and because the arrowhead is defined pointing from node 3 to node 4 is our end node, and node 3 is our start node. So n4 minus n3. So for element 3 will be n4 minus n3, n4 minus n3, n4 minus n3. So x3, y3, z3 are my coordinate difference. So I'll enter this in the function. I'll denote it as k3. K3 is my local stiffness matrix for element 3. I will run. So k3 K3 is calculated now. So this is the K3 matrix. So once you have done this, we should also define our stiffness for the support. The procedure I want to use to solve this problem is the penalty approach. And I'm assuming my last stiffness is infinity, a very large value. And so let KR represent this and that infinity value. So this KR is representing the stiffness of my support, infinity. So that's what this line of code is doing. KR equals to infinity. So this is stiffness of my support, which I'm going to apply to my global stiffness matrix when I assembled it. When I assemble the global stiffness matrix. So as I normally do, the next step is to compute the global stiffness matrix. And how this is done, we need to first define our base matrix, and our base matrix is the zero matrix. And for this problem, because the number of degree of freedom in this problem is 12. We have 12 degree of freedom in this problem. So our zero matrix will be a 12 by 12 matrix. So I create a matrix, a 12 by 12 square matrix, and I assign it to K. K here is representing my global stiffness matrix. I'm going to assemble the global stiffness matrix into this zero matrix. So I run this, you see the 12 by 12 zero matrix. You see it here. So once you have done this, we need to now add K1 to our global stiffness matrix. And what I did, I actually created a vector here, and this vector actually contains the degree of freedom numbering for element 1. I call it B1. For element 1 has 6 degree of freedom. This is element 1. Element 1 has 2 nodes, node 1 and node 4. And node 1 has 3 degree of freedom, 1, 2, 3. Node 4 has 3 degree of freedom, 10, 11, 12. So because the arrowhead is pointing from node 1, so I will start my counting from node 1. So the number will be 1, 2, for element 1, it will be 1, 2, 3, 10, 11, 12. Do you understand? 1, 2, 3, 10, 11, 12. So that is why this B3 here, B1 here rather, that's why B1 here is defined as a 1 column 3, meaning 1, 2, 3, 10 column 12, 10, 11, 12. So this is my degree of freedom numbering for element 1. I actually created this vector because I want to use it to add my K1 matrix. So I want to write K1 at this position in the global system matrix at position 1, 2, 3, 10, 11, and 12 in the rows and column. So if I should write it in this format, this is zero matrix. So B1 for the row, comma B1 for the column is equals to repeat everything here, everything on the left hand side, on the right hand side. Then add K1. K1 is our local stiffness matrix for element 1, which we have already calculated. So once we run this code, you see the K1 matrix gets added to the 12 by 12 zero matrix. We see this is like a portion of the K1 matrix. This is another portion here. And this is another portion here. The 6 by 6 matrix. This is another portion here. And see how Matlab adds the K1 matrix to the zero matrix. We do the same thing for element 2. So what we did for element 1, we do for element 2. We define the degree of freedom matrix. So I'm defining the degree of freedom matrix for element 2, B2. So B2, if you should check our final element model, element 2 is located between node 2 and node 4. And because the arrowhead points from node 2 to node 4, it means node 2 is my start node, node 4 is my end node. So I'll start my numbering or my counting of my degree of freedom from node 2. So it will be 4, 5, 6, 10, 11, 12. 4, 5, 6, 10, 11, 12. So B2 will be 4, 5, 6. So this is wrong. B2 will be 4, 5, 6. 4, 5, 6. 4 column 6, which means 4, 5, 6, 10, 11, 12, 10, 11, 12. So you let me run it, try to update. So this is 4, 5, 6, 10, 11, 12. So we have this here 4, 5, 6, 10, 11, 12. So I will enter B2 in the same manner that I did for K1. KB2, B2 equals to KB2, B2 plus K2. So K2 gets added to the zero matrix in that manner. And we can actually see where it's added. I think this is a portion of K2. This is another portion of K2. I think this is another portion of K2. And I think K2 was added to what was existing. K2 was also added at this position too. So for element 3, the degree of freedom numbering is 4 column 6, 10 column 12. This 4 column 6 means 4, 5, 6. 10 column 12 means 10, 11, 12. But let's check to make sure it's correct. For element 3 is located between node 3 and node 4 as seen in the final element model. And you see the arrowhead is pointing from node 3 to node 4. It means that the start node is node 3, the end node is node 4. So we start our counting of our degree of freedom numbering from node 3. So it will be 7, 8, 9, 10, 11, 12. 7, 8, 9, 10, 11, 12. 7, 8, 9 at node 3, 10, 11, 12 at node 4. So 7, 8, 9, 10, 11, 12. So I'm sure it's wrong, so we need to correct it. 7, 8, 9, right? So this is 7, 8, 9. Yeah, 7, 8, 9, 10, 11, 12. 7, 8, 9, 10, 11, 12. Let me confirm. 7, 8, 9, 10, 11, 12. So B3 is 7, 8, 9, 10, 11, 12. So you write Matlab code in this same manner to add your local student matrix of element 3 to the base matrix. So this is our final global stiffness matrix. Since we have just 3 elements, this is our final global stiffness matrix. We need to add our support stiffness. We need to modify this global stiffness matrix by adding our support stiffness to the global stiffness matrix. In this problem, let's check the finite element model. We see at node 1 we have support, at node 2 we have support, at node 3 we have support. This support means this point cannot move in any direction in the 3 degree of freedom at each of the node. So it is pinned in the x, y, and z direction at those nodes. So it means at direction 1, direction 2, direction 3 at node 1, the stiffness, there is no movement at those 3 directions. At node 2, the same thing. At 4, 5, 6, there is no movement in those directions. At node 3, 7, 8, 9. At node 3, the degree of freedom there is 7, 8, 9. So there is no freedom in the 3 directions. So it means that for 1, 2, 3, 4, 5, 6, 7, 8, 9, we need to add a large stiffness to denote our support at those directions. From 1, 2, 3, 4, 5, 6, 7, 8, 9. At node 4 does not have any support, it's free to move. So no need to add support stiffness at node 4 for degree of freedom 10, 11, 12. But for 1, 2, 3, 4, 5, 6, 7, 8, 9, we add a large stiffness, which is what I did there. At 1 column 1, that is for degree of freedom 1, I added a large stiffness, KR. I already defined KR somewhere in my code. Let me see if I can find it. You can see KR equals to infinity. So I'm adding infinity at 1, 1, because there is no movement at that joint. At 1, 1, at 2, 2, at 3, 3, at 4, 4, at 5, 5, at 6, 6, at 7, 7, at 8, 8, at 9, 9. So once I add the infinity to these 9 positions, I should run. So this K here, So you can see infinity, the infinity that were added. Infinity here, 2, infinity here, infinity here, to position 9. To position 9,9. So this is the modified stiffness matrix. So now we have our modified stiffness matrix. Next thing we need to do, we need to calculate our global force vector, and I'm denoting our global force vector as PS. And because we have 12 degrees of freedom, we start from what I did. I created a base matrix 12 by 1. 12 by 1 is a column vector that contains 12 elements. And in my question, we only have one point load, and that point load points in the Z direction. That is at 12. At 12, the load is 70 kilonewton. And you can see my coordinate system I'm using here. The Z points for this problem. Force pointing downward is negative. Force pointing upward is positive. And this force is in the Z direction. So that is and for the coordinate system at node 4 in the Z direction is 12, degree of freedom 12. So that's why at 12 we need to denote this force at position 12 in the force vector. That is minus 70 kilonewton. So I have minus 70 kilonewton defined here. So this is supposed to be minus 70 kilonewton, but I'm using Newton. So that's why I multiply by 1000. So we have minus 70,000 Newton. This is minus 70,000 Newton. Let's run. So this is our force vector, just contain just one value. So now we can calculate our global displacement vector. Here our global displacement vector is defined as a ds, displacement vector. ds represents the global displacement vector. So the inverse of k multiplied by ps, but we can write it in this form. But let me just write it the normal way I write it. Inverse k multiplied by ps. So if I should run, we get this value as our displacement as our displacement vector. And as you can see, the displacement from 1 to 9 is 0 because we have support at that degree of freedom. So that, which is correct. But at 10, 11, 12, we have 3.0635 times 10 power 5. At 10, we have 4.83. At 11, we have minus 9.6618. At 12. So once we have calculated the global displacement vector, we can calculate the local displacement vector for each element. And so let D1 denote the local displacement vector for element 1, D2 for element 2, D3 for element 3. So D1, we actually extract I can extract the displacement quantity in this displacement vector using my B1 vector. Remember, the B1 is my degree of freedom number. B1 should be 1, 2, 3, 10, 11. So this 1, 2, 3, 10, 11. It's just like writing same thing as writing 1 column 3, 10, 11, 10 column 12. But I already have a vector B1 that denotes this. But let me just leave this like this. So if you run this, we get this. We do the same thing for local displacement vector for element 2. We use the B2 displacement vector, B2 degree of freedom vector. and we get this as our local displacement vector for element 2. We do the same thing for element 3. This is the local displacement vector for element 3. So the reason why we are doing this is actually because we want to use this formula here. We want to calculate the area force in each element. And to calculate the area force, we multiply the local stiffness matrix minus the local displacement vector. K1 is a 6 by 6 matrix which we already have in our Matlab memory. D1 is what we just calculated here, D1, our local displacement vector for element 1. Once we multiply these two, we get the force, we get the area force in the member in the X, Y, and Z direction at each node. So once this is multiplied, we get this 6 by 1 vector. The first three values represent the forces in the X, Y, and Z direction at node 1, while this one, the last three, 4, 5, 6, represent the force at the end node. For element 1, the end node is node 4. So if you want to get the resultant, the area force in the truss element, what we can do, we can just find the resultant of the force at one of the nodes. For this element, let's find the resultant of these three forces. Actually use this code here to find the resultant of these three forces. Like the square root of P1 square plus P1 square plus P1 square. I'm calling out the element at position 1, calling out element at position 2, calling out element at position 3. I should run this, I get 3 times 10 power 4 Newton, which is 30,000 Newton, which is 30,000 kilonewton. So P1 is 30 kilonewton. P2 the same thing. P2 is given as K2 minus D2. So this it gives a 6 by 1 matrix or 6 by 1 vector. The first three is the forces in the XY direction at the start node. The last three is the forces at the end node of that element. For element 2, I think the start node is node 3 and the end node is node 4. So you can also find the resultant of these three forces to get the area force in element 2. So I use this code to compute the resultant force, and I also got 3,000 Newton. I also got 30,000 Newton, which is equivalent to 10,000 kilonewton. Same thing is done for element 3. So this is the area force vector. The first three is the area force at the start node. The last three is the area force at the end node. So if we find the resultant of this, get 50,000 Newton. Get 50,000 Newton. So this is what we have here. So element 1 we have 30,000 kilonewton. Element 1 we have 30,000 kilonewton. Element 2 we have 10,000 kilonewton. Element 3 we have 50,000. Element 1 we have 30 kilonewton. Element 2 we have 30 kilonewton. Element 3 we have 50 kilonewton. This value here. So which is actually what I denoted here in my PowerPoint. 30 kilonewton element 1. Oh, element 2, this is not correct. Element 2, this is supposed to be 30 kilonewton. So this is a mistake. Actually, I made mistake initially when I was doing the computation. This is 30 kilonewton. This is 30 kilonewton. Element 3 is 50 kilonewton. This element 3, this is 50 kilonewton. This is 50 kilonewton. So this is how we use the finite element procedure for solving 3D truss problem on the Matlab with the Matlab program. We have come to the end of this video session now. In my next video tutorial, I'm going to solve this same problem using the ANSYS program. We're going to solve this same problem using the ANSYS program. So I'm going to show you how we can solve this same problem on the ANSYS software. Um, Thank you so much for watching my video. I hope you learned one or two things from the video. Tomorrow or next tomorrow, I'm going to release the video for 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 solving this particular problem on the ANSYS program. Have a nice day. Do have a nice day.